This is a joint presentation by myself and my colleague Sina Masoud-Ansari from the University of Auckland. He couldn't be with us today because, well, I kind of bludgeon off him for free computer science work, and yeah, we couldn't get the funding, but he is very much a part of this work. So density analysis is a common geospatial analysis method that we all use with archaeological data. As we all know, it's used for examining spatial patterns on a variety of scales from site-based to continent-based in some cases. One of the main benefits is that it's a quantitative way to display archaeological patterns and somewhat removes the subjectivity for identifying these. For me, with the work that I do, I try not to display points. To me, it's like displaying a raw point cloud from LiDAR. Instead, densities provide a way to show an easier interpretation of the archaeological data record. However, more and more data that we collect is with consideration of elevation in 3D. And it's when we're looking at excavated material, it's the interpretation between these objects, these points in 3D that become more important, arguably, than 2 dimensions. And this is particularly relevant when we start considering things like formation and post-depositional processes that affect the record that we're interpreting. So there's been much work in recent years on the display of 3D volumes for the interpretation of archaeological deposits. Here are some examples of my own work from COMW in Egypt, the Aboriginal burial site of Runka in Australia, and the site of Hammamet in Egypt again. These are reconstructed from section drawings, and they're 3D reconstructions based on very particular recording strategies. In this case, they were 20 stratigraphic drawings, in this case 6. In this case, there was 115 plan drawings representing 3 centimeter spits, which is just a ludicrous level of resolution for the 60s, but hey, it was done. If you'd like to see any more information on these, I have a poster up downstairs on how these were done. But what they're missing, and you can kind of see it in the Hammamet one, is the relationship of the artifacts to these volumes. What is the relationship of the objects? Often we see sequences developed based on pottery styles, of stone artifact types, even attributed to perceived stratigraphic layers. But what is the actual quantitative meaning of these patterns? There's been some work on 3D point densities before, mainly represented in voxel data, represented outside of 3D environments, represented in 3D environments outside of GIS, and are more often than not represented as 2-dimensional displays of 3D data. Now, when I submitted the abstract for this talk last year, I thought, as we all think, it would motivate me to finish this project in time for the talk. But then I had a baby, so you can imagine, you know where I'm going with this. And we've done great strides. Sina and myself, we've put in as much time as we can, but what I'm going to display to you today is very much a work in progress. So I do apologize for that. So with the type of fieldwork that myself and my colleagues do, we have adopted survey methodology, which has come out of Paleolithic France. This was adapted into survey strategies that have been applied in numerous places in Australia and Egypt. And my supervisor Simon Holdaway and my colleague Rebecca Phillips, this was largely what the type of archaeology they did for going on 10, 15 years. And then we started a project on Great Mercury Island, Ahuahu, on the coast of the Coromandel on the North Island of New Zealand. And all of a sudden we were confronted with excavation again of dune deposits, of midden deposits. Quite complicated stratigraphic layering that what you're actually digging up is not so clear. So we developed a system that allowed us to put our survey methodology back onto the excavation material, but it was somewhat removed from its Paleolithic origins, of where it was applied, not where it's developed. So what we do is we record every object over 2 centimeters in size with a total station. When possible, which is difficult with the sand deposits and our working conditions, we record the maximum axis of stone artifacts for dip and strike. And what we get is a very high density of archaeological material or of data. What you see there is representative of over 25,000 points, I apologize, I did not put a scale on, but we're looking at about 10 meters across here. So very high densities of artifacts. So whereas previously we were looking at objects on deflated surfaces, the excavations have these densities of artifacts that all of a sudden have a spatial depth. Now, you could divide this into arbitrary units and spits based on half a meter, 1 meter, a finer resolution if you would. But what are we actually showing there is the question. Now, to do this, and especially based on stratigraphic layering, is that it takes a predefined notion of what the archaeological record is. This is topsoil. This is a silty loam. This is a deflated sand deposit. This is the Paleodune. And in some cases, these divisions, or the divisions that we see full stop, can be quite obvious, but other times they're very subtle and actually not possible to do in the moment. They're all retrospective, if they can be identified at all. And then assigning functional interpretations to them, or even interpretations as to what they represent, can be subjective at best, particularly when many archaeologists are not specialized geomorphologists. Recording sediments is difficult, as Gavin Lucas exemplifies in his book, in his 2012 book, Understanding the Archaeological Record. A sediment could be described as compact, mid-grayish brown, sandy silt with occasional inclusions, and subangular gravel, some iron panning around the edges of the deposit, or simply a pit fill. Very different levels of interpretation. But what we can identify from different we can identify contexts and layers that look different, but what they actually mean from a formation or occupation standpoint is much more complicated. What I would argue is that looking at the objects themselves, where possible, is a different and arguably more consistent and less subjective interpretation of the archaeological record. Now, wanting to do 3D point densities and doing them are completely separate issues. Here are a few of the challenges that we've faced with the application of such approach. In the first instance, actually having data suitable to such an analysis is a challenge. Many projects will not record on this resolution, especially older, when dealing with older data, but also it requires quite a meticulous approach to the record, which is becoming more common, but historically has not been. The other thing it requires is a very fine resolution of elevation, especially when relative artifact positions. We've spent years working on this. We work on Great Mercury. It is a working farm. Bulls will just come and destroy previous excavations. Datums are just impossible to keep. Anything like this is just very difficult. So we've spent a lot of time trying to get relative elevations between our digs using as any controls we can get, and we're confident that we've got our elevation data between seasons down to approximately 1 centimeter on the X, Y, and Z, which we're quite happy with. So the idea of actually having appropriate data is difficult in different contexts. The other issue is displaying the densities and publishing the densities. 3D PDFs allow us to show the publication of 3D models in publications. We have things like Sketchfab and a whole heap of other things to show 3D data. But this can be difficult because of graphical requirements, the size of the files, a whole heap of other more practical issues. Generating these models, the 3D models, takes a little bit of GPU and CPU, but nothing that's out the range of most modern processors. But the real trick with this, and what I haven't seen many examples of previously, is the integration with other GIS data. So polygons, what have been interpreted as surfaces or divisions, photogrammetry, things like that. So to do this, we developed a workflow with a range of different programs, and I think this is the definition of jerry-rigged. But basically, you start off with a CSV of the point data as an input. That goes through a GraphGIS interface, through a script that Sina helps develop. And that lets you talk about the resolution, change the resolution or density of the output, so you can go anywhere from a millimeter to whatever you want. Obviously, the file size output will vary. Over the size of this excavation, a 10 centimeter resolution is possible, but that's not quite good enough. But for a smaller subset in blocks, about 1 centimeter is a reasonable file size. The output of this process is a visualization toolkit, so VTKs, which are a very horrible 3D output. Nothing reads them, nothing talks to them. But we got a script that gets it into Blender, and with the Blender GIS add-on, which is fantastic, we can get our other GIS data into Blender. Now, my goal is to get this out of Blender, out of this CAD environment, and back into a GIS one, such as GrassQ, even Arc. I'm not fussy. It's just doing that is something I haven't quite got to yet. The other thing is the density output is just a standard distribution at this point, but future work, we're looking at developing it so the methods such as quantile and user-defined spacings can be incorporated into the visualization. So here I'd like to present the results of a preliminary case study from Ahu. So as it's off the coast of the Coromandel on New Zealand's North Island. It has evidence for Maori occupation from at least 1300, and it's some of the earliest human occupation in New Zealand. It has a lot of features, fortified pa, gardening features, and a number of other types, but a large part of the occupation is shell midden or sand deposits, so very complicated deflation formational matrices. The one area that I'll be talking about, Waitapu, or Sacred River, we've been focusing on since 2015. There's a whole heap of different archaeological features, so stone artifacts, pits, post holes, all kinds of things, but no apparent patterning to these features. We are dealing with a deflated surface that very much represents a time average deposit. The main stratigraphic sequence for the area has been described as mainly a modern topsoil with a dense burn layer under it, preceded by a silty sand and then sand deposit. But within these are subtle variations that are only really identified after the main excavation, and we broadly separate them into upper and lower layers. A 3D density analysis was tested first off on this 1x1 pit from the Waitapu area. As you can see, the density is isolated to the most bottom layer, but there's no apparent patterning within this layer that would represent any kind of occupation floor or surface. Rather, it looks like the product of formational processes and artifacts that are displaced from their original depositional contexts. The largest excavation of Waitapu is that of EA64 and EA66, so a large trench that are combined. The division of this excavation was used to the excavation was used to define the upper and lower division. And that was somewhat defined by differences in artifact composition, which, broadly speaking, was fire-cracked rock in the top layer and more stone artifacts in the bottom layer, with no apparent patterning within them. On 2D clustering, nothing really stuck out in terms of densities, apart from what may be attributed to features. And when the layers were dug, there was often interpreted as a mottled layer between these stratigraphic units, and it was up to the excavator to define whether they would attribute an artifact to one unit or the other. So very, quite subjective. So work is still ongoing on this site. This is a rotated 3D image. It's not a 2D slice at the bottom there. But this is roughly a representative of a 2-meter strip through the east-west axis of the site, or northeast to southwest axis of the site. What can be seen is a layer of material that corresponds with the lower, what was called the lower level in the western side. But what happens is over on the eastern side, it becomes the upper, which wasn't identified previously. So these divisions that we based on stratigraphy aren't actually reflected in the objects. So what this means is, well, it's a point of contention for the project because people thought they had this understood and it was something else. But I've been able to add a volume to this like this because the recording practices at the time didn't quite record an original surface the way I'd like. But I'm working on it. But what this density suggests is that, unsurprisingly, it's more complicated than we previously thought, and is probably representative of a range of different erosional and depositional processes that represent a time-average deposit. So I'll skip through a few things. So I've got a lot of future avenues for this work. The first one is the efficient creation of a scale. We have a method to do this. It's just typically when I went to generate it for the image I just showed you, the code didn't work, so I just thought I'd put it as future work. But it's we're trying to make it more robust so that it can be easily incorporated with the range of data and be readily brought into existing workflows. I really want to get it out of a VTK format if I can, just because nothing else reads it, but we're working on that. And the way to query the points, to query density bands, to re-export points with particular density values attributed to them so they can be subsampled and incorporated with other analyses is all future goals. At the moment, this is kind of being done with the GIS interface in a CAD environment. I'd like to get it into a GIS one, but we're still working on that. And when it is completed, which preliminary data, which will be done soon, I'm going to just put it on a GitHub and put it out there. So if anyone would like to try this and improve it, it will be there. But thank you.